Hello. Today we are going to continue our lectures on mechanical systems by discussing a little bit the relationship between the models that we have talking about and the corresponding reality. For the reality, I have brought this little contraption here, which consists of a mass suspended via an elastic band to a spring and to a beam above me. So the elastic band plays the role of the spring, and what we will be doing is we will be examining the extent to which we can capture the essential parameters of simple dynamical systems like this using measurements. So the system at hand is a typical mass spring dashpot system. In this particular case, we have the beam, which is above, and that I can show you briefly. And to the beam is attached what we will consider to be a massless spring. So we will take a massless spring here of unknown stiffness and attached to a mass here. We will assume the mass is point, even though it is clearly not. So, as I said, there is damping attached happening with this system, and so next to the spring I attach a dashpot. Now the position of the system, which I measure as x along the vertical coordinate, is varying as a function of time, and it is varying according to the simultaneous effects of the weight mg and the springs whose stiffness is k and the dashpot whose constant is mu, in such a way that we can write the equations of motion to be mx double dot is equal to, in an idealized world, minus k x minus x0 minus mu times x dot minus x0 dot. Now, in this particular context, x0 would be this quantity here, next to which the mass rests when it is not moving, maybe a little bit above this place. Now, x dot 0 is 0, so we can remove this point, and we are left with the equation m x double dot plus k times x minus x0 minus mu x dot is equal to 0. Now, if we measure x from the position x0, okay, then really we can assume x0 is 0 and neglect this term. This gives us the simplified equation mx double dot plus mu x dot plus k times x is equal to 0. Or, in other terms, x double dot plus mu over m times x dot plus k times x, k over m times x is equal to 0. Now, if we are to solve this differential equation, we are interested in knowing the motion that this thing undergoes. For that purpose, we need to solve this differential equation, which is of the general kind x double dot plus bx dot plus c x is equal to 0. If I erase the previous equations, okay, so I make room to solve them, then I can literally do the following. I can solve for this equation by assuming the initial position, say, is a certain initial position. Okay, so I will say x of 0 is equal to x0, and I will, since I'm interested in doing some experiments, I will assume that the initial speed is 0. So x dot of 0 is equal to 0. Under these conditions, I am left to solve the same differential equation as what we have seen before. And things go as follows. The Laplace transform of this equation is s squared times x minus hold on a second. So we have that the Laplace transform of x dot is equal to minus x0 plus s x, the Laplace transform of x. And so the Laplace transform of x double dot is equal to minus x dot 0 minus s x0 plus s squared x. Okay, so we obtain s squared x minus s times x0. That is for the x double dot term, plus b times minus x0 plus sx plus cx is equal to 0. Now, if I put the x's on one side, I obtain that x times s squared plus bs plus c must be equal to all that is on the right hand side, which is x0 times b plus s Or in other terms, x is equal to x0 times b plus s divided by s squared plus bs plus c. Now, if we are to solve this equation, we see that we have a first order term on top and a second order term at the bottom. Now, in this particular case, we know that the second order term can be factorized as the product of two terms, first order terms, with complex components into it. I can write this as x0 times b plus s divided by s plus j omega times s minus j omega. That is not correct. Let me erase. We can, so saying it again, we can factorize s squared plus bs plus c. If I erase the rest of our equation, we'll come back to it later. Okay. If we erase the initial conditions, we will remember them. And if we erase our reminder Laplace transforms, we get that we can factorize s squared plus bs plus c as s squared plus bs plus c is equal to s plus, let's use a times s minus a. Now, what are those a's? They are the solutions to the, sorry, this is not s plus a, but s plus a transpose complex conjugate. Those a's are the solution to this differential equation. I write the discriminant delta as b squared minus 4c, and we have that a is equal to minus b plus square root of delta divided by 2. And it turns out that for this particular system, delta is less than 0. Okay. So in other terms, what we have is a, and by the way, with this notation, this is not a plus here, this is not a plus there, but instead it is a minus here and a minus there. With that notation, if you write that d is equal to square root of minus delta, we end up having a is equal to minus b plus j d over 2, and a bar is minus b. Sorry, the minus is in front of here. Minus b minus j d divided by 2. Okay? In such a way that we can rewrite this as x0 times b plus s divided by s minus a times s minus a bar. Now, we can rewrite this in terms of a term e divided by s minus a plus f divided by s . Let's do it again. S minus a plus s f over s minus a bar. Now, the computation of e and f, I leave it to you. However, you will soon find that f is equal to e bar. On the one hand. And on the other hand, you will conclude that because of this, these two terms correspond to the Laplace transform of two oscillating, decaying exponential. If you remember what we talked about when we discussed the Laplace transform of growing or decaying exponentials, we said that e over s minus a is the Laplace transform of what? E over s minus a is the Laplace transform of e, a certain number, times the exponential of another number, which is exponential of a times t. Likewise, f over s minus a bar is the Laplace transform of f times the exponential of a bar times t. In such a way that the sum of these two terms will be the Laplace transform of the sum of these two terms. Now, let me make some room. I will try and remember this thing and where it came from. I think that I can erase all this safely. I want to keep the mass spring system handy. As it turns out, it is often not a big problem to forget about some of the past when we are doing derivations involving differential equations. We get that x of t will be e exponential of at plus e bar exponential of a bar t. The best way to manipulate all these variables is to remember that a has this value there. Under these conditions, I can rewrite that x of t is equal to e exponential of minus b over 2 t exponential of jd over 2 t. And likewise for the other term, plus e bar exponential of minus b over 2 t exponential of minus jd over 2 times t. Simplifying things a little more, we can express these terms in terms of sines and cosines. Let me make room for these. And we obtain that let me use this pen. X of t is equal to exponential of minus b over 2 t times e cosine dt over 2 plus j times e sine dt over 2. Plus e bar cosine dt over 2 minus j e bar sine dt over 2. Good. We are almost done. Although painful, this derivation is, by the way, fairly easy to do. I'm going to likewise erase this term. Maybe if I use this, it would go a little bit faster. And now I can go back and write that x of t must therefore be equal to e to the minus b over 2t times e plus e bar times cosine dt over 2 plus j times e minus e bar sine dt over 2. Now, for that particular experiment of interest here, we need to have x dot of 0 is equal to 0, which means that E must be equal to E bar, and this guy is 0. Therefore remains that x of t must be equal to e to the minus b over 2 times a certain coefficient k times cosine dt over 2. Setting t is equal to 0 implies that the k must be equal to x0. Now, to truly understand this system and to link it with real life, we need to link it here and there. We need to link our system to the variable b and d. So for that purpose, I need to erase pretty much everything. Maybe you remember just where b and d come from. And so for that purpose, I will need to keep all this material. Let me erase all this on the one hand. Okay. All that on the other hand. And let me finish by erasing these terms. Again, for the experiment, we start from this. And we want to use the experiment to measure this guy and this guy. Now, for this guy, this is fairly easy. D is the oscillation frequency of the system. Now, if I initialize the system and let go, I can measure the time it takes for the system to oscillate. So we're going to do the experiment of measuring the number of oscillations that these guys go to, and therefore the frequency of our mass spring system. At top, I will simultaneously let the mass go and start recording the with the chronometer. I will count 10 oscillations. 5, 4, 3, 2, 1, go. Okay, so I have counted about 10 oscillations for where the last ones are, by the way, very small. And this seems to have happened over the course of 5.8 seconds. So this gives us a frequency of 10 over 5.8 hertz. That is approximately 10 divided by 5.8 is 1.72 hertz. If we are to go into radians per second, then we need to multiply that by 2 and by pi. And we obtain, this is about 11 radians per second. So d over 2 is about 11, or in other terms, d is about 22. And that's expressed in radians per second. Now, we would like to also be able and measure the value of b. Now, this is not as easy because we are about to measure another time constant. And the best way we can try and do that is by maybe trying to measure the time to half amplitude. What is that? That is the time at which the amplitude of the motion is divided by 2. Notice that we could do the time to 1/2 amplitude or time to 1/3 amplitude. Now 1/3 amplitude would be from here, 1, 2, 3. Okay, so it seems to take 2 oscillations to get to 1/3 of the amplitude. Remember, We start here, we let go, and yes, it clearly seems that if we go to a third of the amplitude, we get there in 2 oscillations. Let's start again. This is the neutral point. This is 1/3 amplitude. This is the original amplitude. And 1, 2, yes. Between 2 and 3. Okay. So maybe we can say 2.5 oscillations. Notice, by the way, that any calculation or any design you do later that requires more precision on the part of your measurements is probably doomed to failures. Now, the frequency is 11 radians per second. We also said it was like 1.74 hertz. Now, the period, the relationship of the period to the time they expand is time is equal to the number of periods divided by the frequency. In that case, the frequency expressed in radians per second. That gives us the number of periods divided by 11. So we have the time is equal to the number of periods divided by the frequency. And it is my mistake because it is not divided by the frequency, but instead divided by the frequency expressed in hertz, which is that multiplied by 2 multiplied by pi. So if we go back to our calculator, we can say that we're going to take the number of periods, the number of oscillation, 2.5, that we multiply by 2, that we multiply by pi, wherever it is to be found, 3.1415 92654 divided by 11, and we obtain about 1.43 seconds. Okay, so that's about the time to 1/3 of a period. How does that relate to this guy that we are still after? Well, you see, we know that at time is equal to 1.43, we have e to the minus b over 2, t must be equal to 1/3. So, if we simplify all this, let's save d for the value it has because it's very important for the future. So for the value it has, we end up having that minus b over 2 times 1.43 must be equal to log of 1/3. or in other terms, 1/3, my mistake. Or in other terms, b is equal to the natural log of 3 multiplied by 2 and divided by 1.43. Now, going back to our calculator, we clear this. It's a 2 multiplied by 3, and we take the natural log. Here we go. We divide the whole thing by 1.43, and we get that b is we see b is equal to 1.54. 1.54. Okay, so this is our final value of b. So we can erase the rest. Maybe not this, but certainly all this. We can delete this. We can delete that. And we can also probably delete well, let's keep it this way. So let's remember that d is equal to minus square delta, so we have that 22 must be equal to square root of 4c minus b squared, or in other terms that something along the lines of, well, let's see, 22 squared. Where is it? Here. So something like 484 must be equal to 4c minus b squared, which is 1.54 squared, 2.37, or that c is equal to 484 plus 2.37 divided by 4. That gives us 484 plus 2.37 equals divided by 4 equals 121. 121. So we're almost there. If you remember, this differential equation was of the kind s squared plus mu over m times s plus k over m times nothing times x0. X was equal to something to the right hand side. Okay, so we have up to the mass of the thing, we actually do have an expression for mu and for k. So all measurement made The mass of this particular battery is 66 grams, or 0.066 kilogram. Therefore, you can get that mu will be equal to B, which we measured to be 1.54, times 0.066, and K, the stiffness, would be equal to 121 multiplied by 0.066. So these are the two questions that characterize our physical system. And the experiment that we have done, together with our solution to differential equations, has given us the means to identify these physical questions without necessarily the best accuracy, but certainly within some decent order of magnitude.